Hello. Today we'll talk about polynomials. Well, first of all, let's give the definition what it is. A polynomial it is an expression consisted of finite number of terms. And each term is a product of a constant and one, maybe more, variables raised to an integer non-negative power. Sometimes we talk about polynomials that depends on one variable. Sometimes we have more variables. Well, for example, 5x squared plus 3 is a polynomial. Then 10xy minus x cubed plus, I don't know, y to the power of 5 is also a polynomial, and so on. We can introduce the concept of degree, and we say that degree of a polynomial is the maximal power of the terms. For example, here we have x squared, so the maximal power is 2, so the degree of this polynomial is also 2. Here, the power of the first term is 2, then 3 and 5. So the degree of the polynomial is 5, and so on. But today, and not only today, we'll talk about polynomials over R, over a set of real numbers. And here we can, first of all, let's talk about monomials. It is a simpler concept. So, So, monomials. Monomial over R is, no, it's just a product of a constant and a variable raised to a non-negative power. For example, 5x squared or 10x to the power of 7 and so on. And if you want to give a name to our polynomial, we need to give this name. For example, this is m. And then we need to place our variable inside brackets. So we can say that m of x, for instance, this is 5x cubed. And this power is a degree of our monomial. And if we are talking about polynomials over R, this is a finite sum of monomials. And again, we can give a name. For example, t of x is 5x cubed plus 10 plus 7. Well, the degree of this polynomial is 3 because we take the maximal degree of all monomials. So now it is 3. Sometimes we're talking about so-called zero monomial. It is just 0. If p of x is 0, it is also a monomial. But in this case, we say that the power of this polynomial is minus infinity. If we take a constant, 7, for example, we can also consider it as a polynomial. And now the power is 0 because we can say that this is 7 times x to the power of 0, and so on. Well, what can we do with polynomials? Actually, we can work with them as with real numbers. For example, we can add them. If we add two polynomials, we need to summarize the coefficients of so-called like terms. Like terms are terms with the same power of variables. So if we want to add two polynomials, for example, p1 of x is x cubed plus 5, p2 of x is minus x to the power plus x cubed plus x squared plus x. And if we want to find the sum of these two polynomials, okay, and this is plus, we need to find all like terms. Actually, we can rearrange the terms in each polynomial because we know that if we change the order of terms, nothing changes. So let's start with the maximal power of our polynomial. So this is 5. Here we have minus x to the power of 5. And here we don't have a term with this power. It means that, and if we don't have a term with the power, we consider that the coefficient of this term is 0. So we have minus 1 plus 0 is minus 1, minus x to the power of 5. Then the coefficient of x to the power of 4 here and here are 0, so this is 0. Then x to the power of 3, x cubed, 1 plus 1 is 2. Then x squared, and then x. Oh, yeah, plus 5. Thank you. If we want to subtract two polynomials, we can say that if we subtract, we multiply one of them by minus 1, and then we add them. So we can say that if we want to find sum or difference, so plus minus, oh, no. I will use another string. So we need to multiply this polynomial by minus 1, and then we again need to add them. Minus 1 by this polynomial is x to the power of 5 minus x cubed minus x squared minus x. So it will be x to the power of 5. Then x cubed minus x cubed is 0. Then minus x squared minus x and minus 5. Oh, plus 5. And plus 5. So, to my mind, it's very easy to add two polynomials. Then, also, we can multiply them. And when we multiply two polynomials, we need to multiply each term of the first polynomial by each term of the second one. So, again, maybe let's take the same polynomials. P1 of x is x cubed plus 5. And P2 of x is minus x to the power of 5 plus x cubed plus x squared plus x. Then we need to multiply each term by each term, and we need to remember that we multiply two monomials. We need to multiply their coefficients, and we need to summarize their powers. So what do we have here? X cubed by minus x to the power of 5 is minus x to the power of 8. Then x cubed by x cubed, x to the power of 6, x to the power of 5, x to the power of 4, then minus 5, x to the power of 5, plus 5, x to the power of 3, x cubed, then plus 5, x squared, and plus 5x. Well, again, very easy. And now let's talk about division of two polynomials. If we want to divide one polynomial by another polynomial, it is a little bit more complicated than addition and multiplication. Let's consider an example. Let's take the polynomial 2x to the power of 5 plus 5x minus 3. And imagine that we need to divide this polynomial by, I don't know, x squared plus 1. So we need to find this ratio. We can use the following algorithm. We write the first polynomial called dividend here. Then we use this symbol, these, I don't know, two angles, two right angles. And here we write x squared plus 1, our divisor. So the first step, we need to divide the first term of the dividend by the first term of our divisor. So we need to divide 2x to the power of 5 by x to x squared. And when we divide two monomials, we need to remember that we need divide their coefficients, and we need to subtract the power of the second monomial from the power of the first monomial. So we divide x to the power of 5 by x squared, and this is 2x cubed. Then we need to multiply this monomial by our divisor, and we subtract the result from the initial polynomial. So it is minus x to the power of 5 plus 2x cubed. Okay, subtract. Minus 2x cubed plus 2x and minus 3. Then again, we need to repeat our steps. Again, we need to take the first term here, minus 2x cubed, and here is x squared. Divide, this is minus 2x. So minus 2x cubed and minus 2x. Minus by minus is plus, so we have 2x plus 2x. This is 4x, and again minus 3. Oh, I'm sorry. This is x, so this is... no. Oh, it's okay. And now we have a polynomial, and the degree of this polynomial is less than the degree of the divisor. It means that here we need to stop, and this thing is so-called remainder. So we can write down that 2x to the power of 5 plus 2x minus 3 is x squared plus 1 by 2x cubed minus 2x, and plus our remainder, plus 4x minus 3. And there is a theorem. It is called the Belu Theorem, or sometimes it is called remainder theorem. It helps us to find a remainder when we divide by x minus alpha, by the polynomial x minus alpha. Something's wrong? Okay. So the reminder of division p of x by x minus alpha. It is important that the coefficient of x here is 1, and this is a linear polynomial, so it's just x minus alpha, is p of alpha. So this is the value of this polynomial at this alpha, at this point. Let's prove it. So we divide p of x by x minus alpha, and for example, let the quotient be q of x, for example. So we can write down that p of x is q of x by x minus alpha, and plus our reminder, let's say it is r. And we need to find this r. And if we substitute alpha instead of x, we have p of alpha is q of alpha times alpha minus alpha plus r. Alpha minus alpha is 0, so we have that r is p of alpha. The Belu Theorem. Also, we can use the following algorithm to find the remainder when we divide by x minus alpha, called Hornets Scheme or Hornets algorithm. The idea is the following. So again, we need to divide p of x by x minus alpha. By the way, using this algorithm, we can find not only the remainder, but also a quotient. So let's say that p of x, again, is q of x times x minus alpha and plus the remainder r. And if the degree of p of x is n, of course, the degree of q of x is n minus 1, because finally, we need to get the same degree as here. And these degrees are, so here we have x, so the degree of this polynomial is 1, so here we need n minus 1. And let p of x be a0, x to the power of n, plus a1, x to the power n minus 1, plus so on, plus a0 times x to, plus an times x to the power of 0, which means just an. And q of x is a polynomial, and the degree is n minus 1. So this is b0, another coefficient, x to the power of n minus 1, plus b1 x to the power of n minus 2, plus so on, plus bn minus 1. So we have n terms here. And now let's say that r is bn. Why not? Now let's consider our equality. Here we have a0, x to the power of n, plus a1, x to the power of n minus 1, plus so on, plus an. And this is b0, x to the power of n minus 1, plus b1 x to the power of n minus 2, plus so on, plus bn minus 1 times x minus alpha, and plus bn. And now, what is the coefficient of x to the power of n? Here and here. Here we have a0, and here we can get x to the power of n only when we multiply this term by this term. So the coefficient is b0. So a0 is b0. Then, what is the coefficient of x to the power of n minus 1? Here we have a1, And here we can get n minus 1 when we multiply this term by alpha and this term by x. So the coefficient is minus alpha b0 and plus b1. Okay, and what is the coefficient of x to the power of n minus 1? No, here it's obvious, n minus 1. Oh, a2, sorry. And what about right side? Again, to get x to the power of n minus 1, we need to multiply this term by minus alpha. So this is minus alpha b1. And here we have b2 n to the power of, or x to the power of n minus 3. Right? And when we multiply it by x, we have x to the power of n minus 2 again. So the coefficient is minus alpha b2 plus, oh, minus alpha b1, this is 1, b1 plus b2, and so on. And when we consider x to the power of n minus k, the coefficient here is ak. And what do we have here? To get x to the power of n minus k, plus bk, and so on. And finally, we have that an is minus alpha bn minus 1. We need to multiply this term by this term, and then we need to add bn. Okay. So now we can find all the coefficients. b0 is a0, b1 is a1 plus alpha b0. Here b2 is a2 plus alpha b2, b1. Here bk is ak plus alpha bk minus 1, and so on. And bm is an plus alpha bn minus 1. So this is our reminder. To use this algorithm, it's very useful to use a table. So here, let's write, in the first string, let's write the coefficients of the dividend. So a0, then a1, then a2, and so on. Finally, we have an. If we don't have x to the power of something, we think that the coefficient is 0. So here we cannot skip this coefficient. We need to write that this is 0. So here is alpha. Now we need to find all the coefficients of b. So here is b0, b1, b2, and so on. And what is b0? b0 is a0. To find b1, we need to multiply b0 by alpha, and then we need to add a1. So multiply this, and then we need, oh, no, not here. Then we need to add this number. So this is b0, a0 plus a1. Then to find this coefficient, again, we need to multiply alpha by b2, and then we need to add a2, and so on. And finally, here we'll have bn, and this is our reminder. Okay. Then there is a concept of a root of a polynomial. A root of a polynomial is a value of our variable such that we substitute this value into our polynomial and we get 0. So we say that alpha is a root of polynomial p of x if p of alpha is 0. So using the Belu theorem, for example, we can say that alpha is the root of polynomial if and only if, no, by the definition p of alpha is 0, and also alpha is the root of polynomial p of x if and only if we can say that p of x is a polynomial q of x times x minus alpha, because the remainder must be 0 here. Okay. So if we are interested in roots of a polynomial, we need to solve the equation. We need to solve the equation p of x is 0. And there are a lot of algorithms, but some of them are too complicated. And mainly we will consider the algorithm for solving a squared equation. So imagine that we have squared trinomial and we need to find the roots of this trinomial. So let's consider the following square equation. Ax squared plus bx plus c is 0. And we need to say that a is not 0. Otherwise, we have a linear equation, but we talk about square equation. Well, we need to solve it. What can we do? Well, first of all, let's multiply the both sides of this equation by 4a. A is not 0, so 4a is not 0, so we can multiply the both sides. Great. So it is 4a squared x squared plus 4abx plus 4ac. And it is 0. And now I want to complete a square. So I will start with these terms. So we have 4a squared x squared, then plus 4ab times x, and I will represent this thing as 2 by 2a by b by x. By the way, 4a squared x squared is 2ax squared. So we have 2ax squared plus 2. I will change the order here. 2ax times b, 2 by 2ax times b. And what do we need to add to get a square? B squared, sure. Yeah. So plus b squared, but we need to subtract b squared right now, and plus 4ac. And this must be 0. So this is a square, 2ax plus b squared. Then I want to take this part to the right side. It is b squared minus 4ac. And now let's consider several cases. The first case, when b squared minus 4ac is less than 0. So we have something squared is less than 0. Can it be so or not if we are talking about real numbers? No, yeah, so we don't have roots. Then if b squared minus 4ac is 0, we have that something squared is 0. It can be only when this something is 0. So 2ax plus b is 0. And from here we can find x is minus b over 2a. Again, a is not 0, so we can divide by a. We have one root. Well, actually, we can consider the situation that we have two roots, but they coincide. Or we can say that we have one root if we want to consider different roots. And the last case, when b squared minus 4ac is strictly greater than 0, we have that something squared is something positive. It means that this thing non-squared is square root of this expression or minus square root of this expression. Let's say that this is capital D, so-called discriminant. And we can write down that 2ax plus b is plus minus square root of d. Again, d is greater than 0, so we can take square root. And from here we can find x. Actually, we have two roots, so we can find two x's. This is minus b plus minus square root of d over 2a. Let's say x1 and 2 because we have two solutions of these square equations. Square equation. By the way, if this expression is equal to 0, we have that x12 is minus b over 2a the same. So actually, we can use only this formula and say that sometimes two roots coincide, sometimes not. Okay. And now let's consider the situation when this b is uneven. So we can say that b is 2k. b is 2k. So we have that ax squared plus 2kx plus c is 0. And we need to find the roots of this polynomial. First of all, we need to calculate a discriminant, d. D is now 2k squared minus 4ac. So this is 4k squared minus 4ac. And square root of d is 2 square roots of k squared minus ac. And x, if d is greater than 0. So now let's consider the case when d is greater than 0. So from here we can find that x1, x2 is minus b, this is minus 2k, plus minus square root of d, plus minus 2 square roots of k squared minus ac over 2a. And now we can cancel 2 in the numerator and in the denominator. So it is minus k plus minus square root of k squared minus ac over a. This is more simple formula. Well, but sometimes it is very complicated to find roots using this formula. But we can use so-called Belu theorem. And inverse Belu theorem. And if we're talking about Belu theorem, let's suppose that our quadratic equation has two roots. Maybe they coincide, maybe not, doesn't matter. So if x1, x2 are the roots of ax squared plus bx plus c is equal to 0, we have that x1 plus x2 is minus b over a, and x1 by x2 is c over a. Well, let's prove it. We remember that x1 is minus b plus square root of b squared minus 4ac over 2a, and x2 is minus b minus square root of b minus 4ac over 2a. So if we want to find the sum of x1 plus x2, we'll notice that these square roots will cancel. So we have just minus b over 2a minus b over 2a. This is minus 2b over 2a or minus b over a. Okay, and now x1 by x2, the product of two roots. We need to multiply this thing. And this will be b squared minus 4ac minus b squared, the difference of two squares, over 4a squared. Now we can cancel b squared, we can cancel vice versa, b squared minus b squared minus 4ac, minus by minus is plus, over 2a, over 4a squared. So we can cancel b squared, we can cancel 4a, and finally we have c over a. So we have proved the theorem. And actually the inverse theorem is also true. Let's prove it. That if we have a quadratic equation ax squared plus bx plus c, and this is 0, and we have two numbers x1 and x2, again, maybe they are different, maybe they coincide, doesn't matter, and we have that x1 plus x2 is minus b over a, and x1 times x2 is c over a. We can say that x1 and x2 are the roots of our equation. So let's prove it. From the first equation, we can find x1. We can say that x1 is minus b over a minus x2. And then we can substitute it into the second equation. And we have minus b over a minus x2 times x2 is c over a. Then I will multiply the both sides by a, and then I will take from the left side to the right side. Or I can say that I can take everything from the left side, from the right side to the left side, and multiply by minus 1. So we have, now let's open the brackets and let's collect everything in one side. We have x2 squared plus b over a x2 and plus c over a. This is 0, and then let's multiply by a. This is x2 squared plus b x2 and plus c, and this is 0 again. So as you can see, x2 is a root of this quadratic polynomial, this quadratic trinomial. The same way we can show that x1 is also a root. We need to find x2 in terms of x1 and then substitute, and we'll get that x1 is also a root of this polynomial. Well, actually, we have Vieta theorem for equations, algebraistic equation of all orders. But the greater order is, the more complicated this formula is. And now let's consider the case when we have when the degree of our polynomial and the order of our equation is 3. So first of all, I want to answer the question in the chat about examples. You will have a lot of examples on your practical classes, so I think that you will not have any problems with it. Now I just want to, actually this is a school program, so I just want to remind you the key themes and prove the key theorems, and that's it. And then on your practical classes you will have a lot of examples, a lot of problems, and you will solve a lot of things. Well, now, about the Vieta theorem for cubic equation. Well, let's consider the equation of order 3, but it will be, for simplicity, so-called reduced equation. We say that an equation is reduced if the coefficient of the highest degree is 1. So let's consider the equation x cubed. So the coefficient here is 1 plus ax squared plus bx and plus c, and this is 0. If we have another equation when the coefficient here is not 1, we can divide by this coefficient and we'll get the reduced equation. So the Vieta theorem for this equation says that if we have this equation 1 and we have 3 distinct roots. Now, again, some of them can coincide, but we have 3 roots, x1, x2, and x3 are the roots of 1. We can say that x1 plus x2 plus x3 is minus a, then x1, x2 plus x1, x3 plus x2, x3 is b, and x1, x2, x3 is c, minus c, sorry. So minus plus minus. And in the Vieta theorem for quadratic equation, we have minus plus. Yeah, so we change the sign. Okay, so let's prove it. Let's find x3 from the first equation. x3 is minus a minus x1 minus x2. Then let's multiply the first equation by x3. And we have x1, x2, x3 plus x1, x3 squared and plus x2, x3 squared and plus b. Oh, equals b x3. So x1, x2, x3 is minus c. We can substitute it. Here we can take x3 squared outside. Here we have x1 plus x2, and it is bx3. From here we can find x1 plus x2. It is x3 plus a. And now let's substitute x1 plus x2 into this equation, and we'll have minus c plus x3 squared. Here we have x3 plus a. No, yes, x3 plus a. One second, please. If x1 plus x2 is minus a minus x3. So we substitute. Here we have minus x3 minus a. And this is bx3. Now I will open the brackets and I will take everything to the right side. And I will have that x3 cubed plus ax3 squared plus bx3 and plus c is 0. So we have proved that x3 is a root of our polynomial, is a root of our equation. The same way we can show that x2 and x1 are also roots of our equation, so I have proved inverse theorem. Sorry. We have 3 roots if this holds. So we have showed that x3 is the root of this polynomial, is the root of this equation. It means that x3 is the root. The same way we can show that x1 and x2 are also roots, so it holds. And via the theorem, let's prove it. Here we have that x1, x2, x3 are roots of 1. And then we need to show that x1 plus x2 plus x3 is minus a. X1, x2 plus x2, x3 plus x1, x3 is b. And x1, x2, x3 is c. So we have that x1 is the root of this polynomial. So we can say that p of x is x minus x1 times q of x. When q of x is a quotient of division p of x by x minus 1. And obviously, q of x is a square trinomial. And we know that using the Vieta theorem, we can show that if square equation ax squared, let's consider reduced square equation x squared plus ax plus b is 0, and if this equation has two roots x1 plus x2, we can show that x squared plus ax plus b is x minus x1, x minus x2. Why? Because if we consider this product, we'll have that this is x squared minus x x2 minus x x1 and plus x1 x2. So this is x squared minus x1 plus x2 times x and plus x1 x2. And we know that if we have two roots of a quadratic equation and x1 and x2, their sum will be minus a and their product will be b. So this is x squared plus ax and plus b. So again, if we have two roots of a quadratic equation, we can factorize the polynomial this way. So if our cubed equation has three roots, one of them is x1, we can say that x2 and x3 are the roots of this polynomial q of x. And we can factorize this polynomial x minus x1, x minus x2, x minus x3. And now let's open the brackets. So again, to multiply two or more polynomials, we need to multiply each term of the first polynomial by each terms of other polynomials. Well, let's do it step by step. I will leave x minus x1, and then I will multiply two other brackets. Each will be x squared minus x3 times x minus x2x plus x2x3. Now I can represent this thing in the form x squared minus x times x3 plus x2. And plus x2, x3. Okay. Then again, we need to multiply two polynomials. This is x cubed minus x squared, x3 plus x2, plus x, x2, x3, then minus x squared, x1, then minus, by minus is plus x, x1, x3, plus x2, x1, and plus minus x1, x2, x3. So now I want to rearrange the terms, and I will have, let's rearrange. It will be x cubed minus x squared. We have x squared here and x squared here. So inside the brackets, we have x1 plus x2 plus x3. Then x, we have x here and x here. So this is plus x, x1, x3, plus x1, x2, and plus x2, x3, and then minus x1, x2, x3. Okay, this is our polynomial. So what can we say? We can say that this with this minus is a. So x1 plus x2 plus x3 is minus a. This is b. x1, x3 plus x2, x1, x2 plus x2, x3 is d. And this is c. And if you want to find the roots of a polynomial and the degree is, I don't know, 5 or maybe greater, the idea is the following. You need to guess one of the roots, and then you will reduce the polynomial. You will have another polynomial with the lowest degree. If this degree is 2, for example, you can use the determinant, for example, discriminant, for example, or the inverse related theorem to find the roots. If this degree is greater than 2, you can try to get another root. And then step by step, you will reduce your equation to the square equation, and you will find all the roots. For example, you can use the Hornets scheme because the Hornets scheme helps us to find the remainder. And if the remainder is 0, you can conclude that this is the root of your equation. But again, more examples you will have on your practical classes. Okay, now I can, well, I think we can stop here with polynomials. And if you don't have any questions, what is the question? Можете показать? Это все не то обсуждают? So if you don't have any questions, let's move to the next topic, complex numbers. Well, actually, you can meet a lot of definitions of complex numbers. Sometimes we say that a complex number is a pair AB, and we have very special formulas and very special rules for addition and for multiplication and so on. But we here will use another definition of complex numbers. We say that Z is a complex number if it can be represented in the following form: A plus IB. And here I is a special symbol. No, A and B are real numbers. A, B are real numbers. And I is a special symbol And we use this notation to show that I squared is -1. And then when we add two complex numbers and when we multiply two complex numbers, we will use the rules for polynomials, but we need to keep in mind that I squared is -1. And all the other things are the same. By the way, this A is real part of a number. And this B is imaginary part. Okay. If we want to add two polynomials, so addition. That one plus that two. If that one is A1 plus IB1 and that two is A2 plus IB2, we need to summarize the imaginary and real parts of each number. Again, we consider this thing as a polynomial. So it will be A1 plus A2 and plus I times B1 plus B2. If we want to subtract one complex number from another complex number, the same, we need to subtract the corresponding parts. So plus minus, oh no, plus minus here and plus minus here. No, here and here. Because again, to subtract means to multiply by -1 and then to add. When multiplication that one by that two, again, we need to consider them as two polynomials. A1 plus IB1, A2 plus IB2. Well, let's multiply. Each will be A1, A2 plus A1 times IB2 plus IA1, B2, then plus IB1, A2, and finally plus IB1 times IB2. And we remember that I squared is -1, so this is minus B1, B2. So the real part, no, as you can see, this is a complex number because we can represent it in this form. This is A1, A2 minus B1, B2, then plus I, A1, B2 plus B1, A2. Yeah, so this is real part, imaginary part. So we have a complex number. Then the next operation, we can find inverse of a complex number. So if we have that, we need to find such, I don't know, that prime or that one, such that that times that one is 1. First of all, let's consider this thing. This that with a line is so-called conjugate. If that is A plus IB, that line or conjugate is A minus IB. So we use this definition to show that this is the conjugate of that. And now let's multiply these two numbers. A plus IB times A minus IB. Here we can use the formula for a difference of two squares. This is A squared minus IB squared, but I squared is -1, so minus by minus is plus, so this is A squared plus B squared. And this is a constant. This is a real number. The imaginary part is 0, so this is a pure real number. So if it means that if we multiply that not by conjugate that, but by conjugate that over this number, we suppose that that is not 0. It means that A is not a 0 or B is not a 0. It means that the sum of their squares is not 0. We will have 1. So that times that over a squared plus b squared is 1. It means that that minus 1, the inverse of our complex number, that is a minus ib over a squared plus b squared. And if we want to write it in the algebraistic form, in the initial form, it is a over a squared plus b squared minus ib over a squared plus b squared. Okay, so we showed that if we have non-zero complex number, we can find inverse of this number using this formula. And the final operation is division. If we want to divide two complex numbers, we can use the following idea. So first of all, that 2 is not 0. So that 1 is a1 plus ib1, and that 2 is a2 plus ib2. Let's multiply the numerator and the denominator of this ratio by a2 minus ib2. Nothing changes, of course, but in the denominator we have the difference of 2 squared, and each will be a2 squared plus b2 squared. And here we have a1, a2. Here we have the product of two complex numbers. So this is a1, a2. Minus by minus is plus, so plus b1, b2. Then plus I. Here we have minus a1, b2. And plus b1, a2. Okay. Then we have not only algebraic representation of a complex number a plus ib, but also other forms. And now let's consider so-called complex plane. So this is complex plane. Here we will, let's say that this is a real axis and this is imaginary axis. And if we consider a complex number that is a plus ib, we can say that a point on this plane represents this z. So here we can find a, this is b, so here is our complex number z. And the coordinate of this point is RAB. But what else can we say about this point? We can use so-called polar coordinates. So we can define each point using the distance to the origin and this angle. The angle between the line segment joining our point and the origin, and the positive direction of real axis phi. So if this is R, so-called modulus of our complex number, and phi, it is so-called argument. We consider arguments from 0 to 2 pi. We can write down that this A is here, right? This A is R times sine phi, cosine phi, and B is R times sine phi, right? So what can we notice? We can notice that R squared is a squared plus b squared. We just square the both equations and then we add them. We have a squared is r squared cosine squared phi, and b squared is r squared sine squared phi. but cosine squared plus sine squared is 1, so r squared is just a squared plus b squared. And if we say that r is a modulus of a complex number, so this is a distance, we can notice that this is a non-negative value. So we can say that r is a square root of a squared plus b squared. We can find this r. And to find phi, we can, for example, we can divide the second equation by the first equation. We can cancel r in this case. Sine over cosine is tangent. So tangent phi is b over a. We can use this thing to find phi. Okay. So it means that we can represent our complex number in so-called trigonometric form. That is a plus ib, but a is r times cosine phi, and b is r times sine phi. Now we can take r outside, and here we have cosine phi plus I sine phi. Now this is so-called trigonometric form, and sometimes it's very useful. Okay. Then let's consider some properties of complex numbers. On the lecture, we will prove only some of them, and the other I think that you can prove by yourselves, or maybe you will consider them on your practical classes. Well, first, the first property, that plus that conjugate is two real parts of that. Then that minus that conjugate is 2i times imaginary part of that. Then that 1 plus that 2, if we find the sum of two complex numbers, and then we conjugate this sum, it is that 1 conjugate plus that 2 conjugate. That then 4, that 1 minus that 2, again conjugate, is that 1 conjugate minus that 2 conjugate. Then that 1 times that 2, the product of two complex numbers, the conjugate of a product is a product of two conjugates. So that 1 and that 2. And if we will find the relation, this fraction is also this thing. So the that 1 conjugate over that 2 conjugate. 1, 2, 3, 4, 5, 6. Then 7. If we multiply that and then conjugate, we will have a modulus of that, 7. Then 8. If we want to find modulus of a product, this is product of two modulus, then modulus of the division is that the modulus of that 1 over the modulus of the 2. Here the 2 is not 0. Here also, by the way. And finally, so-called triangle inequality, that the modulus of a sum is less or equal than a sum of two moduli. Okay, we have 10 minutes left. So let's prove only some of the properties. Well, the first property, if that is a plus ab, that conjugate is a minus ib, so we have this is just 2a, and a is the real parts of our number, so this is two real parts of that. The second property, we can prove it in the same way. So let's keep it now. Now part 3, that 1 plus that 2 conjugate, it is that 1 is a1 plus ib1, and that 2 is a2 plus ib2. Okay, conjugate. This is a1 plus a2 plus I, b1 plus b2, conjugate. And by the definition, this is a1 plus a2 minus I times b1 plus b2. We can represent this expression as a1 minus ib1 plus a2 minus ib2. And this is a conjugate of that one, and this is a conjugate of that two. So we have proved what we need. We can prove number 4 the same way. So again, let's keep it. Then number 5. Number 5, where is it? That 1 times that 2. So again, that 1 is a1 plus ib1. That 2 is a2 plus ib2. Conjugate. Now let's find this product. This is a1, a2 minus b1, b2, and plus I, a1, b2 minus a2, b1, plus a2, b1, sorry. Conjugate, and each will be a1, a2 minus b1, b2 minus I, a1, b2 plus a2, b1. Okay. Let's rearrange the terms. I see that from here and here I can take a2 outside, and it will be a1 minus ib1 and from here I can get b2 outside. It will be minus b2. Here we have b1 plus ia1. And now I can take I outside. So I can say that b1 is 1 times b1, and 1 is minus I squared. So here we have minus I squared, here we have I. So we can take I outside, and we will have a2, a1 minus I, b1. And yes, we'll take I, not minus I, so outside. So minus I, b2, and here is a1 minus a1 minus I, b1. And now we have the same term here, a1 minus ib1 and a1 minus ib1. So let's collect, and we have a1 minus ib1 times a2 minus ib2. Yeah, this is the conjugate of that one. This is the conjugate of that two. So we have proved number 5. Then number 6, the same. No, a little bit more complicated, but actually the same. This thing we have proved when we were looking for the inverse of that. This thing you will prove on your practical classes, and number 9 is the same. But we need to pay the attention to this property number 10, because this is a very important property, the inequality of a triangle. So, number 10. We need to show that modulus of that 1 plus that 2 is less or equal than a sum of 2 moduli. Again, let's say that that 1 is A plus A1 plus IB1, and that 2 is A2 plus IB2. In this case, the modulus of that one is A1 squared plus B1 squared, and the modulus of that 2 is A squared plus A2 squared plus B2 squared. If we want to find the modulus of their sum, first of all, we need to find their sum. It will be A1 plus A2 plus I B1 plus B2. Then, this is modulus squared, and this is also. Then we can find the modulus of this complex number. It will be modulus squared A1 plus A2 squared plus B1 plus B2 squared. And now about our inequality. Here we see that this is something non-negative, and this is also something non-negative. So we can square the both sides. And we will show that that square of this modulus is less or equal than square of this sum. Okay, square of this modulus is A1 plus A2 squared plus B1 plus B2 squared again. We need to show that this is less or equal than square root of A1 squared plus B2 squared plus A2 squared plus B2 squared square root squared. Now let's open the brackets. We will have A1 squared plus A2 squared plus 2A1 A2 plus B1 squared plus B2 squared plus 2B1 B2 here. And here we have A1 squared plus B1 squared plus A2 squared plus B2 squared plus 2 square roots of A1 squared plus B1 squared multiplied by A2 squared plus B2 squared. Okay. Again, we need to compare these two things. First of all, we can notice that we can cancel all squares. A1, A2, B1, B2, A1, B1, A1, B2. And also we have 2 everything. So we have A1, A2 plus B1, B2. And we want to compare this value with the product of 2 square roots. Now let's consider this problem. Well, first of all, if this expression A1, A2 plus B1, B2 is less than 0, we can say that this is always less than this part, because this is the product of 2 roots, of 2 square roots, so it is always non-negative. If A1, A2 plus B1, B2 is greater than 0, we can say that we have 2 positive parts, so we can square them, and we will have that A1 squared A2 squared plus B1 squared B2 squared plus 2A1 A2 B1 B2 here, and here we have A1 squared A2 squared plus A1 squared B2 squared plus B1 squared A2 squared plus B1 squared B2 squared. We can cancel this, and this, and this, and we need to compare this thing with this sum. But we can notice that I will go to the next desk. We can notice that if we take a1 b2 plus a2 b1 and we square this thing, we will have a1 squared b2 squared minus, I will take minus here, yeah. A1 squared b2 squared plus a2 squared b1 squared minus 2a1 a2 b1 b2, and it is a square, so it is always non-negative, so it is greater or equal than 0. So we can say that this thing is greater or equal than this thing, right? We can take it to the right side and make this conclusion. So we can say that this is true. It means that this is also true, and so on. So we have proved the triangle inequality. And okay, so that's it for today. If you don't have any questions, see you next week. Next week? No, with you today, with other students next week. So thank you.